Okay, hello everybody. Can you all hear me? Perfect, thank you. So, yes, my talk is entitled Deep Learning Atlas because I want to take you on a tour of different neural networks and tell you as much about them as I can in a short amount of time. So, in this talk, I will start with a very simple explanation of what neural networks are. I think it may have been Albert Einstein who said that you don't really understand something until you can explain it to your grandmother. So, well, let me just wait a second for the music. So, because my grandmother is dead, I will have to try to explain this all to you, because otherwise it means I can't understand everything ever again. But well, I'll start with this theory of what neural networks are, and I'll continue to explain how they learn, which is really the exciting thing about them. And then we'll cover some topics that are related to specific neural networks architectures, convolutional neural networks, recurrent neural networks, and generative models. So, how many of you work with neural networks? Can you raise your hands? Okay, so just a few of you. I guess this will be good then, because for those who work with them on a day-to-day basis, you may be a little bored, but I may still provide some good ways of explaining things. For the rest of you, this might be interesting. And just a word about me, I work for Intel. I work in the Intel Artificial Intelligence Product Group, where we are developing hardware that will be an accelerator for neural networks. This hardware is currently in development, but it should be coming in a year or two to the market, so look out for that. Okay, let's get started. This is Lieutenant Commander Data. He was an android in Star Trek, and famously, Data had a positronic network in his brain. Now, I have no idea how positrons fit into the picture, but I think that the network in his brain was similar to what we currently know as artificial neural networks. And this is what the first part of the talk will be on, and in fact, what the whole talk is about. So what is a neural network? The best definition I know, well, it's not a definition, but it's an explanation of why they're useful, is this. A neural network is a universal function approximator, which means that it can approximate any function. So what's a function? A function is something that takes input and produces some output. And that means that in mathematics, at least, and functional programming, it's a mapping between some inputs and some outputs. Now, as programmers, we can write these functions and make them produce mappings like this. Give them some input, they produce some output. But the cool thing about machine learning methods, and neural networks in particular, is that they can learn to do this themselves. You don't need to write the logic. The logic comes out of the neural network. So, let's say you have a lot of pictures of food, and you want to answer the eternal question, is it a hot dog or not? You can actually train a neural network to do this for you. So this will be my schematic representation of a neural network, and I'll explain what all the different pieces are. So the nomenclature is down below. I'm not sure if you can see it in the back, but the brown dots in the front are our input layer. Then you have a number of hidden layers, and depending on how many hidden layers you have a deeper or a more shallow network. And finally, you have some output layer in the end. So when you want to have a classifier for pictures, then you can create a network that will take as input a picture and produce as output the two labels, hot dog or not hot dog. And everything that's drawn in this picture is either a number or a mathematical operation. Very simple mathematical operations, I'll go through all of them. The first input layer is labeled here as x. Those will be the numbers from the picture. In my little representation here, there are only 4 numbers, so you can think of them as being the first 4 pixels in the picture. Each one is represented by a number. In the real picture, of course, there would be millions of pixels or thousands, however big the picture is that you want to analyze. But for us here, those are just the first 4. And then the thing marked here as W are all the connections between the input layer and the first hidden layer. These are weights, and these are also numbers. So if you want to, so these are this is the input, these are the weights, and this is something called bias, which is added to neural networks for training. It's like you can think of it like an additional pixel that's always a 1 for that next layer. And if you want to calculate the value of one output in the first hidden layer, or one value in the first hidden layer, then you just have to take all the inputs that are coming to that hidden layer neuron, multiply each number. So I'll just walk up to here. You'll just need to multiply each number coming in from the input by the number that is the weight, and then repeat that for all the inputs and sum that up. So that's the formula on the bottom. And then you also take the bias pixel, multiply it by its weight, and you add that also to that sum. So you sum up the product of all the multiplications of the input values and the weights to get the activation value. Well, in fact, you have to do one more thing in order to have a working neural network. You need to apply an activation function to this sum. And these are a couple of activation functions that are commonly used. The most commonly used one these days is called ReLU, and that's on the left there. That's just a function that either takes the value if it's more than 0 or is 0. So it's just like this flat function on the negative side, or a positive value on the right-hand side of 0. These are slightly more smooth functions, but the ReLU function works quite well. So you just take either a max of 0 or your value to get the ReLU. So it's a very simple function. And actually, why do you need activation functions? The motivation for activation functions comes from the observation of how biological neurons in the brain work. They don't just pass down information in your brain from one neuron to the next. They actually accumulate input for a while, and then after they accumulate enough, after they meet a certain threshold, only then do they fire and they pass this information to the next neuron in your brain. So because of this insight, the people designing artificial neural networks decided to use activation functions. I think the first one they chose was something like sigmoid, but these days ReLU is working just as well. So that's if you take a look at the bottom there, that's the ReLU, that's your activation function. But that's all you have to do. You just have to apply an activation function to the sum of all the products of the inputs by the weights and add the bias term. So it's a very simple calculation, and that's how you get the first value of the hidden layer. And then what you have to do, you just repeat this for the next value and the next value, and you get all the values in this layer. Then you go down to the next layer, and you do the same thing, just not with the input values anymore, but the values coming from the previous layer. You multiply them by this set of weights, the next set of weights, and you get all the values for this layer. And finally, you get to your output layer, and you produce a number. And that's your prediction. So you went from pixels through a number of hidden layers, and at the end you produced some number. In this case, the number is 0.9 for a hot dog and 0.1 for not a hot dog, so we assume that the network with some confidence predicted that this is indeed a hot dog. And that's really how they work. It's just that simple. So the cool thing about them is that they are able to learn, and I'll explain this right now. So let's go back to our prediction, and we calculated some number, but if we want to train a network, we need a data set, a training data set, that contains a lot of pictures that are already labeled. So we have a bunch of pictures of food, and they're labeled either 1 for hot dog or 0 for not a hot dog. And in this case, if we already know the ground truth, the real value that should be, that we want the network to produce for this picture, then we can calculate what error the network is making. So this is the value of the loss that the network produces. Right now, because it was producing 0.9 for a hot dog and 0.1 for not a hot dog, it was producing a loss value of 0.2. Let's say this is a very simple loss function, but it would work if we wanted to train it. So now, if we know this, we know what error the network is making, we can ask ourselves a question: what would happen if I took one of the weights, one of the lines connecting the input and the hidden layer, or anything between any two hidden layers? What would happen if I changed its value? So let's say I took that particular weight and I made that number slightly bigger. If I made that number slightly bigger, I can recalculate the value of my prediction, and I see that actually the prediction got a tiny little bit worse. So the loss function is bigger. The value of the loss is bigger. But what would happen if I actually took the same number and made it smaller? If I made it smaller, now the value of my loss function goes down. So I have to make that particular weight smaller. And if I repeat this for every weight, and then I repeat it for every picture that I have in my training set, and I do this over and over again, eventually I will get that set of weights, that set of numbers that are the connections between the layers that produces the optimal outcome for my training set. And that's it. That's how they learn. Actually, there's a lot more math involved in the field of deep learning, and we don't do this just by looking at every weight. We don't try every combination of numbers because it would take too long. So we have a technique called backpropagation that allows us to compute the derivative of the loss function with respect to every weight that's in the network. And that set of derivatives gives us the gradients, which tell us whether we have to make the weight value go up or go down. And then we just increase every weight by a particular learning rate times this gradient up and down. So it happens more all at once rather than one by one through this vectorized computation. But what is happening is just this. We try to see if the loss function will go up or down if we increase or decrease any weight. And so we change the weights to make the loss function go down. And with this technique called gradient descent, we go down the curve of the loss function, finding the optimal set of weights for our network. So that's how they learn. And that's probably how Data may have been learning during his life. There is a really good course online on Coursera by Andrew Ng called Deep Learning. If you want to learn more about this, it's that course really covers it in a lot more detail than I can. But Andrew Ng explains it very well as well. So with this type of network, data could probably make some simple decisions, like if there was a red alert that he heard, and then he would know to drop everything and go and get to the bridge. But for more complicated things, more complicated tasks, he would probably need more complicated neural networks than just this feed-forward network that I was showing you. So the first one of these I want to talk about, the first architecture that we're widely using these days in the field of computer vision in particular, is called convolutional neural networks. So the way convolutional neural networks work is different because they don't look at the whole picture at once, but instead they scan it part by part. So this is going to be an example of a convolution operation. On the left hand there, you see, again, some pixels of a picture. This is just, on the bottom input data, that's just a picture with two stripes, one stripe of 5s and one stripe of 0s. So if this was a black and white picture, it would be like a gray bar. And in convolution, we use something called a filter, and we apply that filter to a region of the picture, starting at the top left, let's say, like here. And we, again, do some simple calculation. Here we take every pixel from the picture and multiply it by the value from the filter, and we take, for every value in the picture and every value in the filter, we just multiply and add. So once again, we're adding products. So the formula is down there, and that way we produce the first value. Then we slide the filter over by 1 pixel, and we perform the calculation again, producing the next value. And then we keep sliding, producing values, sliding, producing values, sliding, until finally we produce something called a feature map. So what I was doing here was applying the so-called Sobel filter to the picture, and the Sobel filter is something that can detect vertical edges. So as you can see, when I produce my feature map, I have drawn it on the bottom, so I have these values, zeros and a bar of 20s and another column of zeros. I have a feature map showing that there was something in the middle of that picture. And that something was the vertical edge that's in the middle of the input data. So through this convolution operation, I created a feature map showing where in my picture all the vertical edges were. And that's how I can detect this simple feature, vertical edge. If I have more feature maps, I can detect other features. I can detect horizontal edges or edges that go diagonally across the region. So when you're actually training a convolutional neural network, because through the same backpropagation computation, through taking a loss and calculating backwards to your results, you can actually train these networks, and you can train them to detect different features. They will learn different filters that detect different things. So here you can see, this is from a famous publication from 2012 from an architecture called AlexNet. It was detecting edges. These are kind of like Sobel filters, but oriented differently, the black and white pictures. And then the color pictures are filters that detect edges between two different colors. So that way, the network was learning to recognize simple patterns. There's also this checkers pattern there that was kind of detecting probably some checkers pattern in the image. And that's all that is added on top of the simple network to produce a convolution operation. So you can actually create a deep network out of this, meaning that you take a lot of layers and you stack them on top of each other. And this is one of the famous networks that won the ImageNet challenge, I think, in 2014 or sometime. It's called VGG. It was produced by researchers at Oxford. And what it has is an input picture, then a number of convolutional layers. Then this green thing is a pooling layer. It's a very simple layer that simply takes an image and scales it down. So you have a couple of convolutional layers, a pooling layer, more convolution layers, another pooling layer, more convolution layers, and so on and so on. And the interesting thing about this architecture is that with every set of convolution operations, the feature map, the number of feature maps grows. So in the end, you have a very small 14 by 14 feature map, but you have 512 of them. So this means that you're taking a big picture, scaling it down to a small picture, but instead of colors, you're now representing something much more abstract. You're representing ideas. And the final layer is simply a fully connected layer, like we saw in my original diagrams, and that was connected to 1,000 different classes in AlexNet, and that allowed us to that allowed this particular architecture to categorize what was in these pictures better than any other architecture at the time. So the interesting thing about this, if you analyze these convolutional networks, is what they learn. So once again, in layer 1, we have what I was telling you before. They learn to detect simple features of the image. The way this figure works is that these are the filters, and these are bits of image that filter recognizes, that this filter is most activated by. So you can see the 9 filters in layer 1 on top there, and then for each one of them you see 9 examples of something that this filter recognizes. So that's what happened in layer 1. You just detect edges, maybe transitions between colors, or maybe fields of a certain color. But then you go down into the next layer, so you kind of go down into the network, go further down into the network, and you see more complex filters that are being learned. And these recognize more complex patterns, not just edges anymore, now maybe circular shapes or some stripy shapes, or just, geometric shapes of any kind. And then you go further down into the network, and you see that it's learning more and more complex patterns. Not just geometric shapes anymore, but already objects, like wheels of a car, or maybe silhouettes of a person, or, I don't know, legs of some sort, one of these. And as you go down, deeper and deeper into the network, the features that the network is learning are more and more complex. And until finally you see a definite dog detector, a person detector, what is it, a cup detector? Anyway, these are patterns that the neural network learned on its own by doing the simple backpropagation from the loss to the original image, and it learns to recognize more and more complex patterns. So this is pretty impressive that it learns all these things, and it has a lot of applications. It allows us to do quite a lot of things. Image recognition, obviously, that's what I was talking about, but also things like facial recognition, so you can recognize the people, maybe your phone unlocks when you pick it up. It's definitely using these convolutional neural networks. Detecting objects in an image, so showing what's actually inside of an image. is done this way, handwriting recognition, and also some other things that aren't necessarily related to computer vision, like drug discovery, are also being done using CNNs. So these are very versatile and useful networks. So data size, definitely something like this would be needed to get them working, I think. Okay, so next architecture, next set of neural networks. These are called recurrent neural networks. And these are fascinating as well. So let's go back to the original diagram that I had, where you just had an input layer, some weights, another hidden layer, more weights, and so on. And let's just simplify this diagram. So you see below there I wrote W1, W2, W3 for the different sets of weights. Let's just simplify this diagram, so now it looks like this. We're no longer representing each weight separately. Now, each arrow here represents the whole matrix of numbers that are needed to connect all the units of one layer with all the units of the other layer. So, with this simplified diagram, let's draw something like this. We have now as input something that is labeled xt, for time t, and this will be apparent in a minute why. Then we multiply it by a set of weights to produce values of the hidden layer, and then we multiply it by another set of weights to get the result, y hat, which is the prediction we're making at time t. Now the trick with recurrent neural networks is that we're going to add one more connection here. And it's usually in diagrams drawn like this, which is a bit confusing, but what it means is something like this. It means that for every input at time t, we produce an output, but we also take the value coming out of the hidden layer, and we propagate that forward to the next time step. So this is used when working with sequences of any type. So at time t, we have the first number in our sequence, and then at time t plus 1, we have the next number in our sequence. But in order to calculate our y hat t plus 1, the prediction at time t plus 1, we don't just use the value, the input value at t plus 1, but we also use the values that were produced before. So that means that the network kind of can rely on what came before our current input. So it has a form of memory. It remembers what it already encountered before, and it can use that to make its determination of what prediction it will make at the next time step. So that way it can process entire sequences. So let's take an example to make this less abstract. Let's say that we have a 4-letter alphabet composed of just these 4 letters, and each letter is represented by a one-hot vector. So in this case, on the left there, an H would be represented as 0, 1, 0, 0. So there's a 0 for an E, 1 for an H, and 0 for all the other letters. And we feed that into our recurrent network. And what would it produce? Well, if it was already trained, maybe it would produce an E. And then we would give it another input, the next input in the sequence, the next time step, we feed it an E. So now the network knows that it has an input E, but that before it already had an H. So at this stage it could produce an L, and then you see where I'm going with this. We feed it an L, it'll produce an L. We feed it another L, it produces an O. So it can learn to produce words, and we can train it through backpropagation, through the same technique that we were using before. We can train it to learn to produce proper words. We can teach it that after an H-E-L comes another L, and that after that comes an O. And actually, this is not very difficult to do. There are tutorials online that show you how to do this. And you can train a neural network to learn text, learn how we write. And if you feed it all of Wikipedia, then it will learn all of Wikipedia, and it will learn to write Wikipedia articles. And this is one of them, coming from a famous blog post by Andrew Karpathy on the unreasonable effectiveness of RNNs. This is text produced by such a network. Now, if you look at it, it looks like text. It has words. It even has all those Wikipedia markup symbols properly put in place. It just doesn't make any sense. But the network learned what text looks like, and it learned to produce text. It didn't learn the meaning of the text. I guess it would have to be more complex than that. We're not there yet. But it learned to produce text, and that is quite interesting in its own right. So recurrent neural networks are really, really interesting and very powerful, and they can do quite a lot of things. So here's another example of what a recurrent neural network can do. Instead of just going letter by letter, we can give it sequences of, we can give it sentences as sequences of words. We use something called word embeddings for this, so if you're interested, look up word embeddings. So then we give it the value, the embedding representation of each word, and we ask it to produce a value like this, positive or negative. And we can, this is a technique you can use for sentiment analysis. You give it some text, like a review for a film or a restaurant, and it will, based on that text, learn whether that sentence meant, or that review meant, that the person was happy or unhappy with what they were reviewing. So sentiment analysis with recurrent neural networks is quite a powerful technique. Another powerful thing, which I'm sure you've already used if you ever used Google Translate, is machine translation. Machine translation also uses recurrent neural networks, where you take the word embeddings of all the sentences from a sentence. That entire sequence, the meaning of the sentence, is captured somewhere in the weights that are here in this hidden neuron. And then once it encounters the end of sentence marker, it starts to produce output. And it can reproduce the sentence in a different language. So think about it. The meaning of the entire sentence was captured in a couple of matrices of numbers, and then from those numbers reproduced in a different language. So yeah, and it learned all that by itself. So this is very useful. You can use this for language modeling, machine translation, like I said. Also, recurrent neural networks are used for other sequences, so speech recognition or speech synthesis, music composition. These things are all done successfully already using recurrent neural networks, and also other applications such as time series prediction, which may be interesting to some of you, and action recognition. And in the field of biology, I've heard of protein homology detection using RNNs. I'm not sure how it works, but apparently it does. So if Data was a composer, somewhere in his brain there would be musical sequences being written, and those may be using something like recurrent neural networks. So I'm coming slowly to the end of my talk, but I want to tell you that these things that I already said were kind of building blocks for even more complex neural networks that are being developed right now. So you can actually combine them together to produce even more complex and more powerful networks. This is an example of something that can produce captions for a video. So if you have a video, what you actually have is a sequence of images. If you have a sequence, you can think of using recurrent neural networks. If you have images, you can think of using convolutional neural networks. So you can combine them. You can actually use the convolutional neural network to process each image into a representation, a vector of values or a feature map of values that you then feed in as your input to a recurrent neural network. And you teach it one by one by one, each frame of the video. And then when the video ends, what you have is the representation of the sequence of ideas captured right there in those numbers. And you can ask it to produce a description of what was happening in the video. Now, this isn't a real example. I'm not sure if just by looking at those 4 images, a network would be able to produce people racing to the top of sand dunes. But that's the idea. That's what it theoretically can do with this architecture. Another, and I'm not going to do it justice at all, but another set of very powerful architectures are called generative adversarial networks. And this is a whole set of experiments that are being done with different architectures, but the general idea is that you have 2 competing networks playing a game against each other. So you have a generator network and you have a discriminator network in this example. In our case, the generator network will be a deconvolutional network. Now, this is going to be a very simple explanation, but you can think of it like the inverse of the opposite of a convolutional network. So a convolutional network took an image and boiled it down to some numbers. A deconvolutional neural network does the same thing in reverse. So it starts with a set of numbers and it produces an image. What we feed the generator is random noise. So we just give it a random number, and it produces, based on that random number, a fake image. When we first start training this generative adversarial network, this would just be random noise. This wouldn't look like a real picture at all. But we then use a discriminator network, which gets either a real image or one of those fake images generated by the generator. And its job is to decide, is this a real image or a fake image? So you have 2 networks, and each of them has the opposite goal from the other. The goal of the generator network is to produce an image that will fool the discriminator network, whereas the goal of the discriminator network is to be able to tell whether this was a real image or one generated by the generator. And you can actually train them together with 2 different loss functions. One will get a better score if the discriminator gets fooled. The other one will get a higher score if the discriminator actually tells which one is real and which one is fake. But by training them, what you're actually doing is doing both, training a discriminator, but also training a generator to generate realistic-looking images. And in the end, after some training, it gets damn close. I don't have a picture to show you, but these generators produce some realistic-looking images, and these are used in many places for data augmentation, producing more data for experiments. They are used for increasing resolution of pictures. They're doing a lot of, there's a lot of different applications of these networks, so check them out. Okay, this is exactly the amount of time that I had for this talk. So I'm just going to leave you with the overall takeaway that we're not quite there yet, of course, but some things that may be driving an Android in the future, we may already be working on. So thank you.